All right, welcome to section 11.4, the comparison tests. Some series have more complicated terms than we have seen so far. In this section, we will add two tests for positive term series and expand the types of series we can test for convergent and divergence. The comparison test says, suppose that you have two series going on, A sub n and B sub n, with positive terms. If the summation of B sub n is convergent and A sub n is less than or equal to B sub n for all n, then the summation of A sub n also converges. Now, some authors and books, and I also like to do this, too soon, I like to take out the B sub n when I know that it converges, and I want to put C sub n over here. And then also, if B sub n is divergent and A sub n, notice we switch the inequalities around, is bigger than B sub n for all n, then the summation of A sub n is also divergent. So I like to write it this way. D sub n is less than or equal to A sub n. Now the reason I do that is because I look at this statement down here. If the larger series converges, that's C sub n, then the smaller series also converges. That's A sub n. If the smaller series diverges, that's D sub n, then the larger series also diverges. That's A sub n. So when I think of this, I kind of think of this as a compound inequality. This is what's in between my ears. D sub n is less than or equal to A sub n is less than or equal to C sub n. So when I find that similar series and compare it and find out whether it converges or diverges, then I just decide which half I have to do here. Okay? So when we state our answer, we're going to say, okay, converges or diverges because of the direct comparison test, which you can abbreviate as DCT. So we're going to put this in our answer all the time. All right, first example. Does the summation from 1 to infinity of 3n over 2n to the third plus 5 converge or diverge? So we need to find a similar series. So we take our series and we kind of just focus on the leading terms of the top and the bottom because that was the same as what we did when we were finding horizontal asymptotes. We're kind of figuring out the same thing, like what's our equation of the horizontal asymptote, or the limit is kind of what we're doing here too. So focus on those leading terms, simplify that, and I can cancel an n. So it simplifies to this summation. So this is what we would call our B sub n. The original is A sub n. This is our B sub n. So we look at this and say, hey, this looks familiar to me. It has an n squared on the bottom. So if I can put a 1 up on the top, so factor out the 3 halves, 1 over n squared, this is a P series. And P is equal to 2, and that's greater than 1, so this converges. All right, so now I know what my similar series does. We're going to compare it to what we originally have. So here's our second step. So like I said, this is where I kind of think of that as a compound inequality. Well, I have something that converges, so I want this half of it, if you will. So we're going to use this form of the inequality, bring down the original A sub n less than or equal to what we simplified that to. All right, and this is going to be for all n greater than or equal to 1. Well, technically, you can think of this as a proportion. We're going to cross multiply it. So 2n squared multiplies up to the top left, and it stays on the left, 6n cubed. 2n cubed plus 5 multiplies to the upper right, and it stays on the right side. And wait a minute, we have two terms here that are the same. We can subtract that over. We get 0 is less than or equal to 15. This is a true statement. So therefore, 0 is less than our A sub n less than or equal to C sub n. So since that's true, therefore the sum series of our original A sub n function converges by the DCT, direct comparison test. Okay? All right, example number 2. All right, well, as it looks like I start out here looking at this series, I see a potential n is in the exponent. That's geometric to me. All right, so I'm going to start with that sequence. Let's see, let's get rid of the 3. It's a constant, don't need it. Let's get rid of the 5, make it into a 1, so let's factor out the 5. So that's 1 over 2 to the n, which is like saying 1 to the n over 2 to the n, and we can write that as 1/2 to the n power. So that's geometric. Your r is equal to 1/2, which is less than 1, and therefore this series converges. So again, we're going to take this form of our inequality, bring down a sub n less than or equal to our 5 over 2n, and let's solve the inequality. So again, cross multiply 5 times, oh wait a minute, hold the phone. I got 5's in the top of both fractions. Let's divide both sides by 5. That way we have 1's. So 2n times 1, 3 plus 2n times 1. We have 2n is less than or equal to 3 plus 2 to the n power. So subtract over the 2 to the n. If I did say 2n, I apologize. It was 2 to the n power. We get 0 is less than or equal to 3 as a true statement. And therefore, here's the 0 less than our original a sub n is less than or equal to our similar sequence function. And therefore, our original series has to converge by the direct comparison test. All right. Sound good? Good. Glad to hear it. All right, let's go to the third example. Okay. Write me my similar series. I'll pause the video, and then we'll come right back. Once you have it, let's check it. Okay, welcome back. You should get rid of the -1. You should factor out the 1/4. And we have 1 over the cube root. We'll change that to the 1/3 power because now this is a p series. P is equal to 1/3, which is less than 1. This diverges. Okay, so now we have to use this form of our inequality. Take our similar series, that, if you will, 1 over 4 times the cube root of n, and say it's less than or equal to our original sequence. Well, it's good they both have 1's on the top. Quick cross multiplication. And we subtract over the 4 times the cube root of n to both sides. We get -1's less than or equal to 0, which is definitely a true statement. And therefore, since 0 is less than our similar series, which is less than or equal to our original series or sequence formula or function, therefore it has to diverge. Okay? So therefore, our original series diverges by the direct comparison test. All right, example number 4. Again, find me the similar series. So pause, and we'll catch up with you in a second. All right, welcome back. So take the original sequence or series and start to simplify. Get rid of the -4. Cancel some n's, so we're looking at the summation of n equals 1 to infinity of 12 over n. Well, again, that's a p series where the power on our bottom n is 1. That's less than or equal to 1. That diverges. And we've seen before in the past that all harmonic series diverge. So now we're going to use this inequality. So our original sequence function, diverges, not converges. I don't know why I said that. So we're looking at this inequality here. So our 12 over n is less than or equal to 12n over n squared minus 4. If you wanted to, we could divide both sides by 12, or if you just want to cross multiply, doesn't matter. 6 of 1/2 dozen of the other. So in this case, I just went ahead and cross multiplied, which is fine. And notice that we get 12n squared minus 48 less than or equal to 12n squared. Both cancel out the 12n squareds. Negative 48 is less than or equal to 0, so it's a true statement. So since our similar series diverges, then our original series has to diverge. So again, 0 is less than, this is our similar series, our sequence function, less than or equal to our original a sub n sequence function. So therefore, the original series diverges by the direct comparison test. Okay? All right. Let's go to example number 5. Oh, wait a minute. 5 looks just like number 4, but it's got a plus sign here. So, well, let's find out what happens here. Get rid of the plus 4. cancel the ends. It's like, hey, that's the same similar series, which was diverging. I'm not going to goof it up this time. So let's use this inequality, just like we did in the last one. Again, if you want to divide out the 12s and call it 1 over n and n over n squared plus 4, or just cross multiply right away, both are good. But here's something very interesting. Now we have a false statement. Before we had negative 48 was less than or equal to 0. Now it's a positive 48 less than or equal. That's not true. So now we cannot conclude that this diverges yet. We need to come up with a new test. All right, so that will end part 1. We're going to look at our next example. Will be this one again. We're going to come up with that new test.